Okay, so the midterm covers basically everything we've talked about so far in the course. So modules 1, 2, and 3 on basically describing fluid motion, forces and kinematics of fluids, and non-dimensional analysis. So these are everything we've covered in those chapters. The rough time breakdown. Um, so it's mostly long answer with some short answer and some multiple choice. These are my tips for studying for the midterm. So you have a lot of practice options available. There's 5 homework question sets with solutions posted. There are 6 tutorials also with solutions. I have to double check that the TAs have been posting those solutions. And I also released a practice midterm yesterday. So that practice midterm will also be useful for you when you're studying. I'm holding some special office hours during reading week. So on Wednesday, I changed these by the way from what I posted on Learn. So I will update the Learn. So on next Wednesday, I'll be in the office for office hours from 10 a.m. to 11 a.m. But I'm also around here during reading week. So if if that time doesn't work for you, or want to meet some other time, just email me and we can easily make an appointment. The day before your midterm, I think you have an exam until 1:30, so I'm going to be in the office from 2 to 4 that day. And if there's lots of you guys there asking lots of questions and stuff like that, I can always see you later, 2 to 4. And the TAs are also available and happy to meet with you um, by appointment if you don't like talking to me or you just prefer their answers. And yeah, we'll be available for questions on Discord or email. So basically, the story is here. Like we're around if you guys have questions during reading week, just let us know. Okay, so are there any questions about the midterm format, how you can prepare for the midterm, that sort of thing? No? Okay. So let's see. Yeah, in terms of time, I don't think it's really valuable if I read through all these, but what I've done is this will be posted, actually it is posted on Learn. So when I give these kind of summary of last lecture slides at the start of every lecture, I've basically combined them all into this slide deck. So you have basically a summary of every lecture. It's pretty high level. Like there's some stuff definitely you have to work through if you don't recognize this, but this is a good starting point to see all the different concepts we've covered. So for example, lecture 2, what we covered, lecture 3, these are just, I've just pulled out those slides from the slide deck. So you have a nice kind of summary here of all the different concepts we've covered. Okay. I'm going to talk in a little bit more detail of, I guess, some topics that I think are important for your midterm today, but feel free to have a browse through these. Okay. So we're going to start by talking about the different fluid properties we looked at. So fluid properties, we talked about density, the symbol rho, and it's defined as a mass per volume. So some volume, what's the mass inside that volume? Is units of kilograms per meter cubed. We talked about specific gravity. Called that SG. And we said that's the density of our fluid rho over the density of water. So that is going to be unitless because the density units will cancel. We have dynamic viscosity. That is mu. That is units of pascals times seconds, or sometimes it's given in units of poise. We also talked about kinematic viscosity. We said that was nu equals mu over rho. That is units of meters squared per second. I can give you a tip to remember which one is dynamic and which one is kinematic. So mu is kind of this longer letter, right? And dynamic has the y in it, which is a longer letter. So that's how I remember. So like dynamic is mu. It kind of looks like a y. That's how I remember. Okay. So those are the basic fluid properties we talked about. Let's talk about the fluid fields we talked about. Okay, so we talked about pressure. In general, pressure is a scalar field that is a function of 3 different dimensions as units of pascals. And pressure is a scalar field. We say that the scalar field pressure acts in all directions at a point, which means if you take a plane, you get basically it acts normal to a plane. So it acts normal to a surface in all directions at a point. We also talked about velocity, called that v. So in general, v is a vector field that is a function of x, y, z, and t. It has components. In general, each of these components is also a function of all these things. So x, y, z, t, I hat. So u of x, y, z, t, I hat plus v, x, y, z, t, k hat plus w, z, t, k hat. And that is a vector field. Are there any questions about what we've covered so far? Okay. Let's talk about the operators we've talked about. So in our incompressible fluid, we really only have these 2 fields plus our fluid properties. Those are generally considered constants. And kind of the equations, the language of the equations, the operations on these different fields create different forces or represent different like accelerations and things like that. So the operators basically allow us to express it's basically the language of the Navier-Stokes equations are these operators. Okay, so the operators we talked about were divergence. That's represented by, sorry, nabla dot something. We talked about gradient, and that's represented by just nabla something. Can anyone think of another operator we talked about? I think I heard it, but maybe just say it louder, please. Material derivative, yes, that is an operator. So the material derivative we notate as d by dt with capital D. So the material derivative operator, in general, you can take the material derivative of whatever you like, and that will just give you the time rate of change from a Lagrangian perspective, meaning how whatever property you took the material derivative of changes over time as you're following this thing in the fluid. And so that actually requires to actually compute that, you need the velocity field, even if you're not taking the material derivative of velocity. Okay. If we take the material derivative of velocity, we get acceleration, you remember. So that's where this comes in the Navier-Stokes equations. In order to write F equals ma, we need to have the material derivative in there. Any questions about the operators? Okay, good. Let's go to the equations now. So we talked about continuity. Which says that the divergence of the velocity field equals 0. And that is conservation of mass. We also talked about Navier-Stokes. The Navier-Stokes equations are rho times the material derivative of the velocity plus mu times the Laplacian of the velocity field. So actually that's usually notated like this. Okay, so technically the Laplacian is also an operator we could have listed here, but I didn't actually really define what it does. And I'm not going to ask you guys to know what it does in fluids one. So I gave you the form of the Navier-Stokes equation so you could kind of see what it does roughly, right? But we didn't really derive it from first principles. We didn't come across it from first principles. Okay, the Navier-Stokes equations, again, we talked about this, but what conservation law do they represent? Momentum, right. Conservation of momentum. So that's what F equals ma is. It's conservation of momentum. That's what the Navier-Stokes equations are. So again, the Navier-Stokes equations, this is basically ma equals summation of F. They're not exactly equal to all these things. For example, density is not equal to mass, but we kind of get there from this. So in order to derive this, we had to also have like a dV of volume but that dV appeared in every single term. So it canceled out and we're left with something that just has density in it. Okay. So all of the things we've studied so far in this class are special cases of the Navier-Stokes equations. I'll say special cases of NS for Navier-Stokes. Okay, so the first thing we looked at was hydrostatics. So in hydrostatics, with certain assumptions, the Navier-Stokes equations give us P equals P0 plus rho Gy. So if we have some sort of stationary fluid, we draw isobars through it, we get horizontal, evenly spaced isobars, meaning that we have a uniform pressure gradient and pressure varies linearly with depth. Yes? Yeah. So in the next case, which is acceleration, you'll notice the isobars are parallel with the free surface. This is in general not true. But for the special case of hydrostatics and acceleration, the isobars are parallel with the free surface. It's the same thing, like for example, when I did the rotating fluid, the isobars were parabolas as well. So they're kind of parallel with the free surface. It's just like the free surface, you move it down linearly. But like remember when I can't remember what lecture it was. Maybe I can find it here. So in general, like isobars are quite a complicated thing, right? I think at the top of this lecture, did I show you the isobars of um, the atmosphere that day on, yeah. So like these are isobaric lines. So in general, an isobaric line is just a line of constant pressure, but we get really, really nice ones in hydrostatics. So this was on um, January 18th, the isobars in basically the atmosphere over Canada. Yep. So that was hydrostatics. Second one was rigid body motion. And the pressure distribution in rigid body motion was P equals P0 minus rho AX x minus rho G plus AY G plus AYY. So I'm not going to go through it, but remember that the coordinate frames were just defined. One is up and one is down for these two different equations. So just understand how the coordinate frames were defined for these. And if you've done the practice problems, it'll be pretty straightforward to see what the different coordinate systems do to the problem. Just in words, the coordinate system for the first one is defined with P0. P0 is always the pressure at x0 and y0. X equals 0, y equals 0. In the first one, we say that y equals 0 is the free surface, and that y is defined positive downward, so the pressure increases downward. In the second one with the rigid body motion, we used a different coordinate frame, but you get equivalent results either way. So we used one defined here with y positive and x positive. You'll notice that in the case where there's no acceleration, these actually produce the exact same result, just flipped by a minus sign due to the definition of y. So those are the isobars for our accelerating fluid. Any questions about these two special cases? Okay. So the first case, we can remember that we can integrate this for pressure on or forces on a submerged surface. So make sure you go through. I think the performance was like generally pretty good, so I think you guys are good with the forces on a submerged surface. But um, yeah, make sure you do. There's one on the practice midterm. Okay. The next case, maybe does someone know what's another like type of fluid that we studied or special case? What do we move to after rigid body motion? Yep. Quet flow, yeah. So quet flow. So now the fluid, in these two examples, there's no relative motion of fluid parcels. So there's no viscous forces. Everything experiences in the rigid body motion, there is motion, but everything experiences that uniform acceleration. So there's no viscous forces. And in hydrostatics, nothing's moving at all. So you don't have to worry about anything like that. But in quet flow, we have relative motion of fluid parcels. So we can get viscous effects. Quet flow. So we talked about quet flow in the context of understanding shear stress and viscosity. So quet flow, I'm going to just give some equations. So tau equals d du by dy. This is true anywhere for a Newtonian fluid, okay, for the quet flow case. So general shear stress is viscosity times the gradient of velocity. So we looked at quet flow, for example, we looked at a couple different cases of velocity profiles. So say we have a plate here and a bottom wall. With certain assumptions, we get a linear velocity profile. Right? There's also the case we looked at a couple of times, maybe I think it was in the tutorial, rotating cylinder's case also has a linear velocity profile. So the case where both of the plates are moving, we get a velocity profile that looks like this. The actual location of the point of zero velocity depends on the velocity of the 2 points. So in general, it won't be in the middle. It'll look something like this. Okay. The way to go about most of the analysis for this case is to see this. So sorry, that should go that way. So this is kind of our linear velocity profile I'm drawing for the case where both plates are moving. Let me draw this a little bit nicer. Okay, so both plates are moving in opposite directions. Velocity at the top plate, say, is by the no-slip condition, it's to the right. And the same thing at the bottom. No-slip condition, it's to the left. So the thing that allows us to analyze this, or we look at these two triangles here. So some blue triangle, and this green triangle in the bottom. And these are similar triangles. So similar triangles means that, for example, the ratio of this vertical to the horizontal here on this big triangle is the same as the ratio here on the smaller triangle, the vertical to the horizontal. So for example, that's how you find the location of the zero velocity. So the location is an unknown, but you know your total height is got to be this height plus this height. Okay, so any questions about the velocity profiles for these Couette flow examples? Couette flow is, again, not generally true. It's a very, very special case where you have the linear velocity profile. Okay, so we'll talk about shear stress and shear forces and friction forces now. So the linear velocity profile, again, I'm still talking about Couette flow. Means that we have a constant du dy. Therefore, we have a constant shear stress. Therefore, tau wall, which is the wall shear stress, is mu du dy at the wall. That is always true. But in Couette flow, we can just say mu du dy because we only have one du dy. It's constant throughout our fluid. Now to get the force on the plate, this again is generally true. So F, I'll call this F plate. We have to integrate the wall shear stress, which could vary in this case along the plate, dA. So this is generally true, what I've just written. But for the Couette flow case, since we have a constant shear stress along the x direction. We also have a constant shear stress in the vertical direction. So the shear stress is constant everywhere. That means we don't have to do any integration. So all we have to do is do tau A, where A is the area of the plate. Any questions about that? So now we relax some of the simplifying assumptions of Couette flow and we move on to boundary layers. So it's a more complex wall shearing flow. Boundary layers. So we have a nonlinear velocity profile now. So kind of picture you can have in your head of a boundary layer is, say you have some sort of flat plate or flat wall here. There's some sort of boundary layer. We'll go like that. I'll do that in green. Boundary layer goes like that. The boundary layer is, so remember we have this nonlinear velocity profile. So at any given point, the boundary layer thickness, delta, is defined by the u value being 0.99 u infinity. That's how the boundary layer thickness is defined. So the picture you can have in your head is, say you have really like slow Couette flow, um, slow like laminar flow between plates that you can assume is like a linear velocity Couette flow. You start moving those plates like way faster, you get a boundary layer forming on both of those plates. So one kind of leads to the other if you start speeding up the plates. Eventually you move so fast, you can't, it's not laminar anymore, there'll be like turbulence, and you'll get turbulent boundary layers forming along each of those plates. So Couette flow is a very, very laminar case. It also helps that Couette flow most of the time occurs for like a thin gap between the plates. But in general, if the plates are far apart and they move very, very fast, you get a boundary layer. You don't get that linear profile. Okay. So there any questions on what I've talked about so far? So let's talk about now shear stress in the boundary layer. So tau wall is mu du dy wall. So now we don't have a constant du dy anymore in our flow. The du dy changes. So du dy is, like, for example, this line here. So you can see it changes because we have a nonlinear velocity profile. But this statement here is always true. So in a boundary layer, everything basically changes along x. So we start by defining the Reynolds number, Rex. Sometimes it's written both ways, but so that's a function rho u infinity x over mu. So this is a function of x. So the Reynolds number based on x is not constant in a boundary layer. As you move down the plate, the Reynolds number based on x increases. So for some cases that have been studied very carefully experimentally, that means that we can determine, since the Reynolds number based on x keeps increasing down your plate, you can predict, say, oh, at that point you'll have like a pretty laminar boundary layer. And as you go further down, more mixing has occurred, so now it's basically a turbulent boundary layer. So that case is called the smooth flat plate. So if we have a Reynolds number based on x of less than 5 times 10 to the 5, we're in the laminar region. Laminar. We have a Reynolds number greater than 3 million. That means that we can assume fully turbulent. So these numbers here are given for the very special case of a developing boundary layer on a smooth, flat plate. But there are like a million different ways where we can change this. So if you have roughness on your plate, you might just assume the entire thing is fully turbulent. So you don't have to predict the transition point anymore. You just assume everything's fully turbulent. So this is not generally the case. So for example, the practice midterm has you assume, for a part of the boundary layer question, it has you assume that it's a fully turbulent boundary layer the entire way along. Okay, so what else changes with x? So boundary layer thickness is a function of x. So the boundary layer basically grows along the plate. It continues to grow. And the actual thickness itself depends on whether or not we're in the laminar or turbulent boundary layer. So we have expressions that I gave for laminar ones and turbulent ones. Okay. Now what else changes? Remember in the co-ed flow, our wall shear stress was constant along the x direction. So we have the same wall shear stress being applied at every single location along these plates. That is not the case for a boundary layer. So in the boundary layer, the fluid shear stress changes as you move away from the wall, and it also changes as you move along the boundary layer. So the wall shear stress is different at every single point in your boundary layer. And how do we calculate the local wall shear stress? So let's say tau wall is tau wall of x. So it's a function of x. That's 1/2 rho u infinity squared times the skin friction coefficient, which is a function of x. And for that, we also have laminar expressions and turbulent expressions. Any questions about this? So how we can use this now is if we say we have an entirely laminar boundary layer, we can integrate our expression for CF of x to calculate the total, say, F plate or F skin friction. So I'm going to go through something that was an example that was on one of the homeworks where we did this for a laminar skin friction coefficient. And the reason I'm doing this is because in the tutorial when we did the one for the turbulent boundary layer, I think there were some misconceptions on what actually varies along x in this boundary layer, what has to actually be integrated versus what can be just pulled out of the integral. So the total skin friction drag is the integral of tau wall of x times dA. This expression, again, like the one I said, like what I said above. So this expression here is the general case for this. So remember with the flat plate Couette flow, I started for the same expression, but since everything's constant in the flat plate, it makes it easier. Okay. So we get, so I'm going to take the total skin friction drag in a laminar boundary layer of length L. So that is 1/2 rho u infinity squared CF of x. And then dA we replace with w dx. Okay. So we only have one thing in here that's actually a function of x. So CF of x. Remember I said CF of x changes along the boundary layer. So the skin friction at different points is going, the local skin friction value is going to be different. So now we can pull basically everything out of the integral except that 1/2 w rho u infinity squared 0 to L CF x dx. Does anyone have questions on basically what I did to get up to this stage? So now I'm going to replace this again. So we're doing a laminar boundary layer. So I can replace CF of x with our expression for CF of x. And that was 0.664 over the Reynolds number of x. Again, the Reynolds number of x changes along the boundary layer. It's not constant. So it was a common misconception that basically the Reynolds number of x is always, say, 5 times 10 to the 5 for a boundary layer. That's not true. So the Reynolds number of x changes along the plate. It stops being a laminar boundary layer when you hit that 5 times 10 to the x. So Reynolds number of x is a function of x. We can basically write this as, based on the definition of Reynolds number of x, it's rho u infinity x over mu. Now everything in here except x is a constant. So you can do this. What we can do as well is combine some of these constants in the Reynolds number of x with these constants that are out in front. Integral 0 to L of 1 over x to the half. So this is a relatively simple integral, but this is basically how you find the force on the plate by integrating the skin friction coefficient. The analysis is very similar for the turbulent boundary layer. The only thing that changes is, say, like this constant on top changes and also the exponent in the bottom changes, but you still just get an integral of x to some exponent. Okay. So any questions about this? Yep.
If you had a question where you had to do like you had to get the drag for a surface, and then at one point it transitioned into turbulence. Would you do two integrals and add them together to get the total thing, or would you do one integral throughout and you do something different?
In general, yes, you could do that, but the expressions the way I've given them now, the definition of these expressions doesn't really work like that. So you have to do a little bit more analysis. You might do this in fluids too, like to do that. So basically, it's a good question. So we asked, say you have a boundary layer, a developing boundary layer. Some part of it's laminar, some part is transitional, some part is turbulent. How could you estimate the total on that? So with the expressions and all the examples and everything we've done so far, you can't. So you can basically only estimate a fully laminar or a fully turbulent boundary layer. Okay? So good question though. Okay. So if this was confusing for you, I highly recommend you go through this example you've done on the tutorial. You did the turbulent case. The example on the homework was the laminar case, also the one I've shown here. So I'm going to give some hints now on dimensional analysis. Okay. So for choosing the repeating parameters, which again is the hard part, often a Buckingham pi. So make sure you see the lecture 19 notes. I've given very clear general rules of what you can use there. I know the homework is a little bit confusing and that sometimes the general rules aren't followed, but make sure you look at the lecture 19 notes. You need J repeating parameters. Remember, J is the number of dimensions in our problem. They need to contain all dimensions. So if you pick if you have mass, length, and time, and you only pick repeating parameters with mass and length in them, that's bad. You need to have mass, length, and time in your repeating parameters. It's a green flag if your resulting pi groups are starting to look like the ones in that table. That means, okay, I probably picked the right repeating parameters. So verify that your resulting pi groups look like common ones. And again, table 5.2 is going to be provided. On the midterm. So the practice midterm has like that table provided in it with the material properties. That's exactly how it will look like on the actual midterm. Are there any questions about any of what I just said?